Welcome back, you guys, to another Tutor Toby video. So, in today's video, just like the title reads, we'll be going over some applications of first-order differential equations. Specifically, we're going to be going over brine tank problems. Yes, I wrote brine tank problems twice because it is the bane of all first and second years who are taking their first ordinary differential equations course. So, let's get into it. Okay, so first off, we ask, what is a brine tank problem? So basically, we just have a brine tank, so a giant tank, with a hole or a pipe in the bottom that has some flow going out, and then we also have a hose going in, if you know what I mean, or something like that, which has a flow in at concentration equal to C. So this can be in like molarity or like grams per gallon or something like that. And then we also have a volume V of this brine tank. Okay. So now what we do is we just kind of give values to these. So I'll do a specific example. So let's say our flow in is equal to 100 gallons per minute. Let's say that our concentration in is equal to 10 grams per gallon. Let's say that our volume is equal to 1,000 gallons. Let's say that our flow out is also equal to 100 gallons per minute. So notice how I have flow in equal to flow out. So this is like a specific type of brine tank problem, which is like the simplest one, which is why we're going over it first. Okay. So now we ask, well, how can we kind of turn these into like an equation that we can solve? So we'll say that we want to find the stuff in the tank. So this could be like some salt or like sugar, something like that, as a function of time. So in order to solve this, we make a differential equation, and then we can just solve the differential equation. So we first say, okay, so my change of stuff in my tank is going to be equal to, at some really small amount of time, so like in a really small dt amount of time, it's going to be equal to the amount of stuff coming in minus the amount of stuff going out. Okay, so now we ask, what is our stuff in? So my stuff coming in is just going to be equal to my flow coming in times my concentration coming in. So this makes sense because if we just look at the units of this would be gal per minute times concentration, so that is grams per gallon. So then we get a unit of grams per minute. Okay? So now that we have, I will keep that on the screen. So now that we have that, we know that our stuff in is just going to be equal to 100 times 10, which is equal to 1,000 grams per minute. Okay? So now we ask, what's our stuff coming out? Well, it's going to be the exact same as above. It's going to be flow out times concentration out. Okay, so we know what our flow out is. That's the same as above. That's just that. But now, what's our concentration going out? So our concentration going out is going to be equal to the concentration of our tank, right? Because it's going to be mixing all up when it's in here, and then it's going to be going out. Okay, so we know that the concentration of our tank is just going to be the stuff in my tank divided by volume of my tank. So in this case, the stuff in my tank is what we're trying to solve for, remember, right up here. So we have stuff tank all over volume of my tank. So what's my volume? It's going to be this 1,000 right here. So we have 1,000. So now we can actually make a equation, and we can actually solve this equation. So let's just call stuff in tank, let's define it to be tank. Let's define it to be x. Okay, so this equation from up here turns into x prime, right? Because this change is just the same as a d. If it's really, really small, it's just going to be a dt or a dx. So it's going to be dx over dt. So that's just going to be x prime is equal to my stuff in. So my stuff in is just 1,000. And then my stuff out is going to be 100 times, so we have this right here, 100 times x over 1,000. Cool. So now we notice that this is actually in my integrating factor method form. So we say x prime plus, what is 100 divided by 1,000? So that's going to be x over 10 is going to be equal to 1,000. Okay? So now we say, okay, this is in the form y prime plus p of t x, or y in this case, is equal to f of t. So our integrating factor method is e to the integral 1 over 10 dt. So that's going to be e t over 10. So now we multiply that on each side. So e t over 10, x prime plus x over 10. Okay, and then by the magic of integrating factor method, since this is in a specific form, we know that this is actually equal to d dt e to the t over 10 times x, which is still equal to our e t over 10 times 1,000. And then to get rid of a derivative, we can just take an antiderivative, an integral on both sides with respect to dt. So then this turns into e to the t over 10 times x is a function of time, is going to be equal to, what is the integral of this? So that's just going to be 1,000 times 10 e to the t over 10. And then since it's an indefinite integral, we always add a plus c. Okay, so now we can just divide over, so we get our x as a function of time is equal to 1,000 times 10 plus c all over e to the t over 10. Okay, so now what is this c right here? Well, remember, we need an initial condition, so we can't really know the amount of stuff in our tank unless we know what we started with. So let's just say that we have an initial condition of concentration initial in our tank is equal to, let's just say it's half of what's going in. So that's going to be 5 grams per gallon. Now, here's the thing. We do not want our concentration initial. No, because we're solving for our stuff in initial, right? So we have to convert this into an initial amount of stuff. So we know that concentration times volume is equal to stuff, right? If we just look at the units, so this would be grams per gallon times gallons is equal to grams. So we just look at our units and we know that that equation works. So we can say 5 times 1,000 is equal to my x at time t equals 0. So this is going to be 5,000 equals x at 0. Okay, so now we can plug this back in over here and get 5,000 equals 10,000 plus c over e to the 0. What is e to the 0? Well, that's just 1, so that's equal to c. So we get c is equal to minus 5,000. So then we get our final answer, which is x at time T is equal to 10,000 minus 5,000, and then I'm just going to pull this up to the top, e to the negative T over 10. And this is going to be our final answer. So now we know the stuff in our brine tank as a function of time. Okay, so now that we have a relatively simple brine tank problem done, let's do one where we have, let's just do the exact same one, except instead of having our flow in be equal to our flow out, let's have our flow out be equal to half of our flow in. Okay? There's nothing special about a half, but let's just choose it to be, relatively easy for calculating without a calculator in front of you guys. So we do the same thing. So we know stuff, so the change in stuff is equal to, at a really small, at an instantaneous amount of time, is equal to stuff in minus stuff out. So this is going to be the same as last time, where our stuff in is going to be flow in times concentration in minus my stuff out. So that's, again, just going to be flow out times my concentration of my tank, right? Again, because it's mixing and then going out like that. So now this is where it's a little bit of a trick. So what's my concentration of my tank? Well, again, just like last time, it's going to be equal to the stuff in my tank divided by volume. So the weird thing is here, my volume as a function of time is not a constant, right? Because we know that my flow in is not equal to my flow out. So obviously, my tank's water level will slowly be increasing over time until it starts to overflow. So what is my V of T? Well, it's just going to be V initial plus time times change in flow. So this change in flow, I mean as my flow in minus my flow out, right? So if we just look at so we could always like miss a negative here. So for a quick sanity check, we know that if my flow in is greater than my flow out, my tank water is going to be rising, which is what this gives. So we know that we have the right negatives. Okay? But now we know what V is as a function of time. So we can plug this V back in up here. So this goes to stuff or concentration in my tank is going to be equal to stuff in my tank, which, remember, this is what we're trying to solve for, divided by, so this is going to be 1,000 plus T, my flow in minus my flow out is going to be equal to 50, so T times 50. Okay, so now we do the same thing where we say stuff in my tank, we'll just call it the variable x. So then we get from up here and right here, we get that my dx dt, so my x prime is equal to, well, what's my flow in times my concentration in? So again, that's just going to be 1,000. So then we have the second term, which is flow out. So my flow out is going to be equal to 50 times my concentration of my tank. My concentration of my tank is just given right here. So this is going to be stuff in my tank I called X, remember? 50 times T. Okay? And now, again, this is why I solved it using integrating factor method last time, because it's a great method, because we can use the same thing over here. So we get X prime plus 50 over 1000 plus 50T times X is equal to 1000. Okay? So we get e to the integral of 50 over 1000 plus 50t dt. So what is this integral equal to? It is going to be equal to a logarithm, right? And then we see that this 50 and this 50 would actually be good, or like cancel out if we made a u sub. So we get e to the natural log of 1000 plus 50t. Cool. What's really cool is that this e and the natural log cancel each other out. So then we get 1000 plus 50t. Awesome. So we multiply this on each side. So we get 1000 plus 50 times t. I will just copy and paste this from right here. Times the group right here. So now, since this is in our specific integrating factor form, we know that it just goes to d over dt times our integrating factor, which is just equal to 1000 plus 50t times our x, which just is awesome every time how it works out like that. So that equals 1000 times the group, 1000 plus 50 times t. Okay? Get rid of the d dt. We can just slap on an integral on each side. So we get 1000 plus 50t times x is going to be equal to. So what's this integral? So that's going to be 1000 times the group, 1000t. Should say dt over here, right? Because we have to integrate with respect to t. So 1000t plus 25t squared. And then we always have plus a constant. Awesome. So now we can just slap over a divisor on this side. So we get x as a function of t is actually equal to 1000. 1000 times t plus 25 t squared all over that right there. And then we still have plus a constant divided by, again, this right here. Cool. So now this is our kind of general form. So if we want the specific form, again, we say, what is my x at 0 equal to? So my x at 0 is going to be equal to, what was it up here? So I'll just reuse it. It was equal to 5,000. So we say it equals 5,000. And remember how we had to find that? So we get 5,000 is equal to, let's see, we plug in 0 here, and we plug in 0 here. So both of those terms are going to be 0. So we have 0 over 1,000. So that's just going to be 0 plus c over, how convenient, 1,000. So then we get that our c this time is equal to, oh man, I should put this in exponential form, or scientific. 5 times 10 to the, oh geez, 6. So we have 3 zeros here and 3 zeros here, so it turn out to be 6 zeros. Cool. So c equals 5 times 10 to the 6th. So then we get my x of t is just going to be the same as up here, except now my c is just equal to 5 times 10 to the 6th. Awesome. So now what we can do is a lot of the times these problems ask what's the amount of salt in our tank before our tank overflows. So we can say tank has a total capacity of, let's just say 2,000 gallons. So what's my stuff in tank as it just overflows? Okay, so in order to find this out, we ask, well, when does it overflow? Well, this is pretty easy, right? We know from above, we already had to solve for our volume with respect to time, right? That was right here. So I'm just going to copy and paste this. Copy, paste, arrow and everything. So yeah, we know that our tank overflows at 2,000. We know that our initial amount of like brine in the water is 100. And then we have time. We're trying to figure out our time. We know that our flow in minus our flow out is going to be 50. So then we can easily solve for time. So this is going to be 1,000 divided by 50, which is equal to, what is that, 20? 20. So 20 minutes. So now we say, well, what's the amount of stuff in my tank just as it overflows? So now we already know my time. So now it's just asking basically, what is my x at 20? So if we plug this in, we get all this stuff up here. And then instead of x, or instead of t, you just plug in t equals 20, and we have our answer. Awesome. So now we know how to solve a brine tank problem when our flow in is not equal to our flow out. And it's basically the exact same steps as our original one. Alright, you guys, thank you so much for watching. Remember to like, share, and subscribe if you found this video entertaining, maybe, or if you learned anything. You probably don't need to hit the notification bell, as I have videos coming out relatively sparsely, and they'll all be going over the same stuff. So if you're later in the in your differential equations course, it'll be a little bit too late. But anyway, remember to like and share, comment if you found it useful, and I will see you on the next video.